Okay, y'all, hanging with Hussick once again. As promised, I will show you how to work through a heat or enthalpy of reaction problem. So heat is always designated by Q in chemistry. Sometimes it's lowercase q, sometimes you see uppercase Q. I'm going to draw an uppercase Q, but lowercase q will be all the same. And enthalpy generally is designated by delta H. Sometimes it's referred to as the enthalpy change, and basically it means the heat change quantified in kilojoules per mole of whatever is reacted or whatever is physically changed. Alrighty, so here's the question we're going to tackle. Calculate how much heat is released by the complete combustion of 206 grams of hydrogen gas. And it gives you the data value for that, the enthalpy of combustion for hydrogen. You should also be aware that a lot of these enthalpy of combustions, enthalpy of neutralizations, enthalpies of reaction like this, they are found in the IB data booklet. If you're an IB student working through this and you're looking for these values, or of course you can Google most of these and find them if they happen to be not given and the situation lends itself to that, but obviously on a test you can't. So the enthalpy of combustion for hydrogen, as it says here, is minus 286 kilojoules per mole. So that means when you burn 1 mole of hydrogen gas, it releases 286 kilojoules of energy. So this is heat released. We know that because the value is negative. Okay, the delta H value is negative. That tells us it's heat released. It also tells us that technically this is an exothermic change. Okay, it's exothermic. We should know that as soon as it says combustion, we should realize that it's exothermic. The other thing we should realize in the context of this question is that when we're writing out the equation for what's happening, and you should always try and do that, we have hydrogen plus oxygen turning into H2O. Okay, so when you combust hydrogen gas, it only makes water. It doesn't actually produce any carbon dioxide because there's no carbon. This is part of why burning hydrogen is considered a very clean fuel. It's considered, potentially one of the fuels of the future. So to balance this, you put a 2 right there and a 2 right there. Okay. What I was saying though is we should realize that because it's combustion, it's always exothermic, and also because it says in the context of this question, the complete combustion of 206 grams of hydrogen gas. We're assuming that all of that 206 actually is combusted. We don't have to worry about what the limiting reagent is in this case, stoichiometrically. We're going to assume that hydrogen gas is going to be the limiting reagent for sure. That's kind of the flavor of this question, okay? So let's solve it. So the first thing we have to do is find the moles, convert the mass to moles, okay? Once we convert the mass to moles, then we can apply that per mole, that heat released per mole, and calculate the actual amount of heat released. Because it's really important to remember that the delta H will fall in line with the molar ratio. In other words, like if 1 mole is burned, we're going to release 286 kilojoules, okay? So let's convert that mass to moles. So we do that through the formula moles is equal to mass over molar mass for hydrogen. The mass given is 206. The molar mass is going to be 202. 2 hydrogen atoms. Punch that into your calculator and you should get a value of about 101 point something or other, depending on how many figures you keep. I'm going to keep 0.98 at this point, and I'm going to round it to 3 significant figures at the end because that's how many is given in the question, okay? So we'll round it at the end. We have 101.98 moles of hydrogen gas. Now what we do is, step 2, we convert that into heat, okay? So we apply the molar enthalpy of combustion, is what it's technically called, for hydrogen, and figure out how much heat is released. and determine heat released. Because the heat released, we aren't necessarily burning 1 mole, right? We're burning much more than that. So in this case, the heat is going to be equal to the number of moles that we burned times the delta H for this process, all right? And we can go ahead, like, we know it's heat released, so we can go ahead and like leave the positive or negative off of it, you know? We know it's heat released. It's just going to be a quantity of energy in kilojoules, and we know it's released. So we're going to take 101.98 or whatever. If you kept the big dirty number in your calculator, just use that. And we're going to multiply that by negative 286 kilojoules released per mole. That's per mole of hydrogen gas, okay? And this really here, I should have put the unit moles of hydrogen gas, because then you'd see that they actually cancel out, and you end up with a value in kilojoules. And if you put that into your calculator, what is that value? It's around 29166 kilojoules. That's a lot. That's a lot of hydrogen gas, actually, in this question. It's like kind of like a little hydrogen bomb. Now, if you wanted to actually write that properly in 3 significant figures, as the question dictates up here, you could, being a real fancy Nancy, write 2.92 times 10 to the exponent 4 kilojoules. Okay? And you would have that baby solved and sewn up. Oh, I realized I didn't do what I said I was going to do and leave the negative value off it. I put it on and then I just ignored it. But we know it's heat released, so you can just say, yeah, you can just, realize it's heat released.